Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello students, let us solve the next question. Question number 30 of JEE Advanced Physics paper 2015. So let us solve with question number 3030. Hello students, let us start with question number 30, which is given as follows. An ideal monoatomic gas is a monoatomic gas. This monoatomic is confined in a horizontal cylinder. This is a cylinder by a spring-loaded piston. This is a piston and a spring attached to it, and the other end of the spring is connected to this one, this fixed support. I suppose this is fixed because this has to move in this direction only. As shown in the figure, initially the gas is at temperature T1, pressure P1 and volume V1. So its initial pressure is P1, V1, T1, the pressure, volume and temperature, and the spring is in its relaxed state. Spring is in its relaxed state means that there is no extension or compression in the spring. So then the gas is then heated very slowly. You have to heat it slowly to increase temperature to T2, pressure to P2 and volume V2. In this new situation, your pressure is P2, volume is V2, temperature is T2. During this process, the piston moves out. So this piston moves outward by a distance x. So it moves by a distance x. So it will be its new position here, somewhere here. It will be its new position. Ignoring the friction between the piston and cylinder, there is no friction between the walls of the cylinder and piston. The correct statements is or are, which of these statements is or are correct? So first of all, we have to see the statement and then solve. The statement number 1 says that if V2 is 2V1, that means you have heated to so that this volume becomes double. The final volume is twice the initial volume, and temperature is 3 times. Whatever is the temperature here, this temperature is 3 times that of the initial temperature. Then the energy stored in the spring is 1/4 P1V1. So we have to first find what is the energy stored in this case. If that matches with this option is correct. So if I see that initially you have a diagram like that, you have a piston and a spring over there. Here the pressure is P1 and here whatever is the atmospheric pressure or whatever pressure is there, so it balances with that. Here the pressure is P1, so here also the pressure will be P1. So therefore there is no, this is in equilibrium and it is in relaxed state. And this distance I call x0, suppose, when the spring is in its natural state. And in the second case, when it is heated, it moves to a distance. So this is the extension x1, say x1 is, or x, say x is given x, so I'll write x here. This is x, and initially it was x0. Total extends distance is x0 plus x. So this is the extra distance the piston moves forward. Now again, when it is in equilibrium, the spring is obviously compressed, so spring will also exert a pressure in this direction. there will be a spring force in this direction. So therefore the pressure I'll write as, if V2 is given under the condition that V2 is V1 and T2 is 3T1, under the condition that P2, in this second situation the pressure is P2, and obviously this pressure P2 is a combination of the pressure due to 1 and due to the spring. This P2 must be the pressure what was inside and the pressure due to the extension of spring. So therefore this pressure P2 I write as P1 plus, and what is the pressure? This is the force per area, and that is Kx is the extension, compression of the spring divided by the area. This P2 is P1, the pressure was there, plus the extra pressures here. Now, what about, we have to write this X, eliminate X also. We have to find the energy stored in the spring. The energy stored in the spring, is given by half Kx square. Because X is the compression, the spring is compressed by distance X. So this is the energy stored in the spring. So this will write as half Kx square, and we have to find the value of Kx. So from here I will find Kx, and one X will be there. This is nothing but Kx into X. So this is given by Kx, half Kx into X. Now this expression I will take first and write this P2 is P1 plus Kx over A. So from here Kx is P2 minus P1 into A. Then I have to write P2 in terms of P1. So then what I'll do, I have to use the condition that and also write the value of X. The volume, here the volume V2 is, what is the volume? The volume V2 is A into X plus X naught, and the initial volume was A into X. So V1 is the volume, which is A into X. So X I can write as V1 by A. There's no doubt about that. And I have to write this expression in terms of P1 V1. So I'll write in place of X, I'll write this one in the expression for energy, and this P2 is to be replaced in terms of P1. So this I've got 1, and I'll replace this P2. We know that P2 V2 by T2 is P1 V1 by T1. So from here I can get P2. P2 is T2 divided by V2, and P1 V1 by T1. Now this I can write as P2, which is T2 over V2. T2 is 3 times T1. This is given in the question, that in option A, T2 is 3 times and V2 is 2 times. So I'll put this here, 3 times T2, T1, and this is 2 times V1, and this is P1, V1 and T1. So this T1, this T1, this V1, this V1 will cancel out. This will give me 3 by 2 P1. This is how I'm getting it. So from here, if I put this P2 is 3 P1 by 2 over here, and then I'll get Kx. So from here the Kx, by substituting this value over there, this Kx expression will come out to be Kx. Kx now can be written P2, which is 3 by 2 P1 minus P1. into A, which is obviously 1 P1A by 2. This is what I got kx, and x I have already got, which is V1 by A. So x is V1 by A. Energy stored is half kx square, that is kx into x. So the half into kx is P1A by 2. X is B1 by A. A will cancel out. This is P1 B1 divided by 4. So energy stored in the spring is P1 B1 by 4. So if I see this option, V2 is 2V1, T2 is T1, then energy stored is P1 B1 by 4, which is correct, because we are also getting P1 B1 by 4. So this is correct. Now let us move to the option number B, because it is multiple correct type question. The second option B, I have to check if V2 is 2V1 and T2 is 3T1. That means under the previous conditions only, change in internal energy is 3P1V1. So it is see the change in internal energy of the system. So then I have to see the change in internal energy in the case of B. So the option B talks about that volume is double, the temperature is 3 times the same condition, and you have to find the change in internal energy, and we have to match with the. So first of all, we'll find the change in internal energy. The change in the internal energy can be obtained as F by 2 nR delta T. This is the formula for change in internal energy, where F is the degree of freedom. Because it is F is monoatomic, so it is 3. So I'll put 3 here, 3 by 2 nR delta T. An ideal monoatomic gas is taken, an ideal monoatomic gas is confined, and nothing is mentioned whether it is 1 mole, 2 mole, whatever it is. The change in internal energy 3 by 2 nR delta T. We know that PV equals to nRT, so P so the nRT, so final P2V2 is nRT2, P1V1 is nRT1. So then the change is this minus this is the change. nR delta T will be obtained here. So this 2 minus this 2. So delta T is nR delta T. nR delta T is replaced by this value. So it is 3 by 2 P2V2 minus P1V1. Okay, you got this? P2V2 minus P1V1 is this minus this. This is delta T. So therefore this is replaced by this. Now to get this, I have to write the answer or search the answer in terms of P1 V1, because the answer is in terms of P1 V1. So I'll replace or change P2 V2 and write in terms of this P1 V1. P2 I have already got that P2 is 3 by P2 I got last time, which is 3 by 2 times P1. So I'll put that directly here, 3 by 2 P1, and V2 is double. V2 is 2V1, so it is 2V1 minus P1V1. This 2 and this that 2 will cancel out. This 2 and this 2 will cancel out. This is 3 P1V1 minus P1V1. That is 2 P1V1. And that 2 and this 2 will cancel. and you'll have 3 P1 V1. Okay, this is 3 times P1 V1 minus P1 V1. It is 2 times P1 V1. This 2 will cancel. P1 V1 is left, so it is 3 times P1 V1. So the change in internal energy when the temperature changes from T1 to T2 is this, 3 times P1 V1. And in the option, this is given that 3 P1 V1, so this option is also correct. So option number B is also correct. So this is also correct. Next we'll move to the option number C and C, whether that is correct or not correct. The option number C talks about, what is that option number C? The option number C talks about if V2 is 3 times V1. So what is C? V2 is 3 times V1 and temperature is 4 times T1. Then work done by the gas is this. So you have to find the work done by the gas. Okay? Work done by gas to find. When the gas is expanding, it is expanding against the forces, like the force in the spring force, and so the gas is expanding against the spring force, and right, and also the pressure that is outside that piston. So if I talk about this, then this is the whatever is the extension in that case, because the pressure and the volume and temperature are changing, but whatever is the displacement of this. So there is a spring which is compressing it, so spring force is acting, and also there is the pressure whatever it was there. So against these two there is a movement of this piston. So work done has to be negative. So I'll write negative work done, and that work done is due to the combination of, this is due to the pressure outside whatever it is that, and this is due to the work done by spring. The work done by this one is pressure was P1 outside, because initially it was P1 balanced with outside P1. So from here it all is moving forward. So we'll consider this P1, and because the pressure is P1 initially, it is the force is P1 into A. And how far it is moving? It is moving through distance x. So this is the work done by due to the P1 pressure. Again, the work done by spring is plus of, how much is spring work? This is half kx square, so it's half kx into x. Okay, half kx square, and this is P1 ax, and we have to also write the answer in terms of P1 V1. So P1x plus half kx, but then this kx we have to find out, and this x also to find out. How to find out that? In this situation, the volume is while this moves by x, the volume here is 2v1 by a, because the volume has to be how much? It is P1 ax plus work done due to spring is half kx square, which is kx into kx, and x here is 2v1 by a. Why it is 2v1 by a? Because initially the volume, it was x naught, now it moves to x suppose. So here this change in volume, initially the volume was v1, finally the volume was 3v1. So the change in volume is 2v1, and this is the change in volume, and the change in volume is area and this x. So x is 2v1 by a. Similarly, so this x is x I can write as 2v1 by a over here. But what about kx? So again about kx, I'll write here, I'll write kx is what? We know that this pressure P2, which is P2, I'll write in terms of P1, P1 V1 by T1. This is P2 minus P1 is our kx divided by a. This is what is the pressure difference, and this P2 I'll write as P2 is I'll write here P2 V2 by T2 is P1 V1 by T1. So P2 is T2 over V2 P1 V1 by T1. What is T2 given? T2 is 4 times and V2 is 3 times. 4 times T1, 3 times V1, P1 V1 T1. This V1, this V1, this T1, this T1 cancels. So this becomes 4 by 3 P1. So P2 I got as P2 I got 4 P1 over 3 minus P1 is this one, kx over a, kx over a. So this is P1 by 3. Okay, so write P1 by 3 is kx over a. So from here kx is P1a divided by 3. This value of kx that I got here, I'll substitute here and here. The kx I got is P1a by 3. So this is P1a by 3, and this x I got as 2v1 by a. This a and that a will cancel. This is 2, this 2 and this 2 will cancel. P1 b1 by 3 plus P1 ax. So work done by the gas is P1 ax plus P1 b1 by 3. P1 b1 by 3. This is that I got from the last expression, putting those values. P1 ax is again x we have already calculated, is 2b1 by a. That also I'll substitute here. So this is P1a 2b1 by a plus P1 b1 by 3. This a that will cancel, 2 P1 b1. These 3 2s are 6. 6 plus 1 7. So 7 P1 b1 by 3. So work done by gas I'm getting as 7 by 3 P1 B1. 7 by 3 P1 B1. This is also correct. So these 3 options are correct. So now we'll move to the fourth option. Let us see whether that option is still correct or not correct. The fourth option is what? You can see the question. The fourth option is V2 is 3V1, T2 is 41. That means the condition remaining the same. The heat supplied to the gas is this one. Let us check whether the heat supplied is that one or not. We know that for option number D, the heat supplied to the gas using first law of thermodynamics. that the heat supplied is increase in internal energy plus the work done by the gas. The increase in internal energy that we have already got, but here in this case the increase in internal energy will be different because work done is okay, but then increase in internal energy will be different because that was, you cannot take this as the internal energy that we've got earlier because the temperature of 3T1 here is 4T1. So to find separately what is the work done by the gas that I've already got in this situation is 7 over 3 P1 that already I've got this, and change in internal energy I have to find. The change in internal energy can be represented as F by 2 nR delta T, which is F by 2 P2 V2 minus P1 V1. This is 3 by 2 because it's monoatomic. P2 V2 minus P1 V1. P2 we got in terms of P2 in terms of P1. P2 we got in terms of P1. How much that we got in terms of P1? I have to see where I wrote that. Okay, this one. P2 is 4 P1 by 3. So it is from here 4 P1 by 3, and V2 is V2 in the question is 3 V1, so it is 3 times V1 minus P1 V1. So from here this 3 will cancel, 4 minus 1 is 3, so 3 is 9 by 2, it is 9 by 2 P1 V1. So I write this over here, 7 by 3 P1 V1 plus 9 by 2 P1 V1. So if I take the LCM, this will be 2 is multiplied as 14 P1 V1 plus 3 27 P1 V1 divided by 6. So this is 30 41 P1 V1 divided by 6. This is what I'm getting actually, 41 P1 V1 by 6, and in the question it is given 17 by 6 P1 V1. It is not 17 by 6 P1 V1, it is 41 by 6 P1 V1. So option number D is not correct. So option number D is not correct. It is not, it should not be 17, it should be 41 P1 V1 by 6. So therefore this option is wrong, and only these three options A, B, C are correct. Okay, thank you.